Everybody, welcome. Okay, welcome to today's seminar, online seminar. It is Zhaoting Wei from Texas A&M University Commerce, who will speak about Grothendieck-Riemann-Roch theorem, superconnections, and index theorem. Please, sure thing.
Thank you. Thank you for the introduction. And thank you for inviting me. Yeah, today this is my topic, Grothendieck-Riemann-Roch theorem, superconnections, and index theorem. Although maybe this topic itself is not exactly in non-commutative geometry, but I believe that the ideas and technologies, techniques, and some source is closely related to non-commutative geometry. So I think it's suitable to talk about it here. This is a joint work with Jean-Michel Bismuth and Xu Shen, and we have published it as a book in the Progress in Mathematics series. I think it's volume 347, last November. Okay, and today I think we have an hour and a half, isn't it? That's the
Closer to an hour. Yeah.
Okay. Yeah. So I think we have enough time. So I will try to give some backgrounds and also details. So I will try to make it accessible. Okay, first, let's just state the main result. We are talking about a compact complex manifold without boundary. But besides this, we have no assumption on the manifold. We don't assume it's projective or K or even scalar. And let K0x be the Grothendieck group of coherent sheaves on X. We will explain it later. And maybe the third object is not so familiar to us. H equal BC is the Bott-Chen cohomology group of X. We will define it later. Okay. So, and the point is we can define a Chen character map through Chen-Wei theory is the Chen character map from K0, the Grothendieck group, to the Bott-Chen cohomology class. And moreover, for a holomorphic map between compact complex manifolds, we can define the direct image map on both the Grothendieck group and the Bott-Chen cohomology. And then we are asking whether the Chen character map satisfies the functorial property with respect to the push forward. And the answer is no, but we need to modify it by the Todd class. So this is the result we are going to prove. So that's the push forward of the Grothendieck group and push forward of the Bott-Chen cohomology. They commute, but up to we multiplies on the Todd class. Yeah. So this is the Grothendieck-Riemann-Roch theorem we are talking about. Okay, before we move on to details, let me explain that actually the key part of this theorem is a version of the family index theorem by Atiyah and Singer. And the proof our proof uses the heat kernel method. And in particular, the most general case uses the heat kernel method of hypoelliptic Dirac operators. And of course, if X and Y are both projective complex manifold, then the problem reduced to the algebraic case and is the classic Grothendieck-Riemann-Roch theorem proved by Grothendieck. And but that's slightly different because the classic Grothendieck-Riemann theorem, the Grothendieck-Riemann-Roch theorem, the Chen character map is from K0x to the Chou ring. And here we don't have Chou ring, we have the Bott-Chen cohomology class. Yeah, but the ideas are similar. And on the other hand, if Y is just a point, so the right vertical side is just a point, then this result reduced to the Hirzebruch-Riemann-Roch theorem for a single manifold. Okay, so this is the statement of the main result. Then let me move on to the setup of the theory and the proof. First, I think it's good to give some background before we talk about coherent sheaves. So if we just consider a C-infinity manifold and a C-infinity vector bundle, and for connection on it, we can just take the square of the connection that gives the curvature. And the Chen-Wei theory is just the Chen character of this vector bundle is the trace of the exponential of the curvature normalized by dividing by 2 pi I. And this characteristic form is independent of the choice of the connection. So the cohomology class, of course, is independent of the choice of the connection. So this is Chen-Wei's theorem. And of course, if the connection is unitary, then the Chen character form is a real form. Okay, so that's classic Chen-Wei's theorem, Chen-Wei's theory. Now we come to holomorphic vector bundles. And we know that we can study holomorphic vector bundles using C-infinity method because we have the Koszul-Lagrange theorem. That states that on a complex manifold, a holomorphic vector bundle is the same as a C-infinity vector bundle together with a flat d-bar connection. So d-bar means it's from the section of C-infinity section to omega 0, 1, and flat means its square equals to 0. Okay, so for a holomorphic vector bundle equipped with this d-bar connection, and if we impose an emission metric on the vector bundle, then we can find the conjugate of the d-bar connection. That's we get a D connection, which is compatible with a d-bar connection. And so the sum is called the Chen connection. And the square of the Chen connection is not 0, although the d-bar part and d part both squares to be 0, but the commutator of the prime and double prime is non-zero. So it has also a non-trivial square, and yeah, it's the curvature of this Chen connection. And of course, the Chen character defined in this way, it satisfies the previous result. So it's a closed form and it's real. But since we are talking about holomorphic vector bundles, we have a little bit more. So this result is proved by Bott and Chen in almost 60 years ago. So that is, if we have different choices of emission metrics, then the difference of these two Chen character form, they differ not just by the round boundary, it's differed by a dd bar of gamma. And they actually constructed this gamma explicitly. And okay, so this difference of the Chen character is differed by the dd bar of some forms. Okay, in this sense, we can define a refined invariant rather than rather than the Ram cohomology. So that is the Bott-Chen cohomology. So the Bott-Chen PQ is the Ram closed PQ form quotient by dd bar form. And we can talk about the Bott-Chen cohomology, and the Bott-Chen equal is just the direct sum of Bott-Chen PP. Okay, and this has a conjugation of complex numbers, so we can talk about the real subspace Bott-Chen equal XR. And Bott-Chen's theorem states that the Chen character as a Bott-Chen cohomology class is independent of the choice of the matrix. Okay. Yeah, so this gives us some idea of Bott-Chen cohomology and Chen character of a single holomorphic vector bundle. And let's talk a little bit more about the Bott-Chen cohomology. So that is yeah. There is a canonical map from Bott-Chen to the theorem cohomology. And if X is a Kähler manifold, then there's a so-called dd bar lemma in complex geometry. So we can prove that actually Bott-Chen cohomology and the theorem cohomology are isomorphic. But in general, if the X is not scalar, then these two are different. So there are some subtle relations between Bott-Chen and the RAM cohomology. And this Bott-Chen cohomology is functorial with respect to pullbacks and the holomorphic maps. But how about how to define the push forward? The point is, yeah, we can also define the Bott-Chen cohomology class using currents instead of differential forms. And currents, that's the generalized function that's dual to differential forms. And using this definition, we can just define the direct push forward map on the Bott-Chen cohomology class. That's one part of the story. So let's go back to the previous page. So we said that we have a push forward map from Bott-Chen X to Bott-Chen Y. Yeah. So that's the bottom horizontal line of the square. Okay, so this is the push forward of Bott-Chen. So far, is there any questions? Okay. Let's move on. Okay, so the next thing is Cauchy complexes of holomorphic vector bundles. So in the viewpoint of Koszul-Lagrange theorem, a Cauchy complex of holomorphic vector bundle is the following data. So that is a z-graded C-infinity vector bundle, E dot. And now each EI, we have a flat debug connection. And it satisfies the compatibility condition of the Cauchy map V. So we can put it together to make it V plus lambda EI double prime is square equals to 0. And this is an example of anti-holomorphic flat superconnections because it has two directions, a horizontal direction and a vertical direction, and it squares to be 0. By the way, I will talk a more general version of this in later soon. So yeah, so we don't need to spend too much time on this. Okay, so and of course we can input an emission metric on each component E dot, and we can find the conjugate of the V, which is V star, and we can find the conjugate of the connection lambda. So it's lambda EI single prime. So we put them together. So it gives a Chen super connection, and its square is the curvature. And this curvature is not necessarily in omega 1,1. But we can still talk about its so-called super trace and its Chen character. By the way, super trace means we take the trace, positive trace on even degree EIs, and we take the negative of the trace on odd degree EIs, and we sum them up. Okay, so we can define the Chen character in the similar way, but using this A instead of just single lambda. And Bismuth and Gilly and Soulé, they proved in the 1988 paper that this Chen character is also a theorem closed and independent of the choice of the matrix when we consider it a Bott-Chen class. And yes, and it also is actually in the Bott-Chen cohomology it equals to the alternative sum of the each individual Chen character of each component. Okay, in particular, if the Cauchy complex is exact, then the Bott-Chen cohomology is automatically 0. Yeah, no matter how we choose the so-called the connection. Yeah. So the proof is just by just reparametrization. So we reparameterize the matrix. Then under this reparametrization HT, the A becomes square root of T V plus V star A. Then yeah, we just compute the Chen chain character and let t goes to infinity. So it gives the result 0. Okay, so far that's some classic work. And now we are talking about coherent sheaves. What is a coherent sheaf? First, we notice that the category of holomorphic vector bundles is not good because usually, even we have holomorphic morphism between holomorphic vector bundles, is kernel and co-kernel are no longer holomorphic vector bundles. So this category is not so good. So we are thinking about a more general concept. That's a coherent sheaf. A coherent sheaf of OX modules is if it's a sheaf of OX modules satisfies two conditions. First is locally is a finite type. And second is for any morphism from a finite direct sum to F, the kernel is also a finite type. So with these two conditions, we can easily show that the kernel and co-kernel of any morphism between coherent sheaf is also a coherent sheaf. So this is a better concept. So in short, the category of coherent sheaf is a abelian category. So that's much better than the category of holomorphic vector bundles. And moreover, we have this OCAS coherence principle here. It says that if we have a complex manifold and OX is the structure sheaf of holomorphic functions, then OX itself is coherent. This result is not as trivial as it looks to be because it's not so easy to show that OX satisfies the second condition of coherent sheaf. That is, if we put F to be OX, and for OXN, any holomorphic morphism from OXN to OX itself, the kernel is of finite type. That's not so easy because the sheaf OX holomorphic functions is not a Noetherian ring. So yeah, a lot of complicated things may happen. So actually the OCAS coherent principle is just says that although this OX is not Noetherian, if some behavior is not too far away from Noetherian. So yeah, we can still show that OX is a coherent sheaf. And using this, we can get the result that any finitely generated locally free sheaf is coherent. So which means that for finite dimensional holomorphic vector bundles is holomorphic sections, the sheaf of holomorphic sections is a coherent sheaf. And of course, for coherent sheaf, more than holomorphic vector bundle, we have ideal sheaf, skyscraper sheaf, a lot of other sheaves that are coherent but not locally free. So locally free is inside coherent. Okay, is there any question so far? Okay, let's move on. So we can talk about the bounded derived category of coherent sheaves. That's one of the main topics in algebraic geometry. The objects are bounded complex of OX modules with coherent cohomology sheaves. And morphisms, we don't talk about too much, but we just say that we invert all quasi-isomorphisms. And this derived category is a triangulated category. And we can talk about its Grothendieck group. And we can show that the Grothendieck group is the same as the Grothendieck group of coherent sheaves. Oh, maybe. Yeah, I forgot. Okay, so I didn't. So I just say, okay, the Grothendieck group of the bounded derived category, we just define it to be the Grothendieck group of the manifold K0x. So actually, we can define K0x just using a single coherent sheaf, but we can show that these two are isomorphic. So anyway, we just talk about, we have the Grothendieck group of a complex manifold. And moreover, if we have a proper holomorphic map from X to Y, then we can talk about its derived push-forward functor from dB coh X to dB coh Y. And then it induces a homomorphism on the Grothendieck groups. That's app lower Shrek. So it's K0x to K01. Okay, so that's the definition of the derived push forward of the Grothendieck group. Let's move back to the statement of the results. The upper horizontal map is also defined. Yeah. Okay, then let's try to talk about the vertical maps. The first thing in our mind is coherent shifts and complexes of holomorphic bundles are not too far away because we have the Syzygy theorem. It says that for any coherent shift, we locally has a locally free resolution of it. And of course, it doesn't hold if X is singular, but we're talking about complex manifolds. So yeah, everything is regular. So this Syzygy theorem always holds locally. But the problem is it doesn't exist globally. So yeah, there is a counterexample given by Vazan. It says that for a general complex tori with dimension greater or equal than 3, the point shift on the complex tori, which is definitely coherent, is not quasi-isomorphic to any bounded complexes of finite dimensional holomorphic vector bundles. Yeah. So the locally free resolution doesn't exist globally. That's a problem. One thing we can do is we can define another Grothendieck group, just the Grothendieck group of holomorphic vector bundles. We call it G0x. And actually, yeah, this is standard notation in algebraic geometry, K0x and G0x. And one is the Grothendieck group of holomorphic vector bundles, or the Grothendieck group of locally free shifts, and the other is the Grothendieck group of coherent shifts. So these two, in general, are not isomorphic, and it's very difficult to describe their relations. And Bismuth and Gilles-Soulet, their result, it shows that the Chen character defined by them gives a map from G0x to the Bott-Chen cohomology class. Yeah, but the problem is, can we define a Chen character map from K0x to the Bott-Chen cohomology? Yeah. Yeah, this is a problem we will solve. And the solution for us, our solution using the anti-holomorphic superconnection. Now, first we define the anti-holomorphic superconnection on a complex manifold. It's a differential operator. Yeah, satisfies of total degree 1 and satisfies this Leibniz rule. It's the D-bar Leibniz rule. And super means this A double prime, it has a lot of components, which is V0, lambda, V2, and V3, and so on. Where Vi is valued in omega 0I, but the degree on the vector space part is 1 minus I. So the total degree is 1 for each Vi. And lambda is a holomorphic connection on each Vi. So we see that Vi, all the Vi's, they commute with multiplication of functions, but lambda isn't. Okay, so this is the reason that why we don't denote lambda by V1. So we say that we have V0, V2, V3, but we don't have V1. The reason is lambda and all the V's are slightly different. All the V's are just smooth forms, and lambda is a connection, it's a differential operator. Okay, and so we have a picture to illustrate the idea of V0 and lambda and V2 and V3 and so on. So we see that a superconnection has a lot of components, but the total degree is just 1. Okay, then what's a cohesive module? Yeah, a cohesive module is a Z-graded C-infinity vector bundle together with a flat anti-holomorphic superconnection. With flat means A double prime squared equals to 1. Okay, what does this condition mean? So the single equation A double prime squared equals to 1, actually, since A double prime has so many components, this condition A double prime squared equals to 1 has a lot of components too. The zeroth component means V0 squared equals to 1. V0 squared equals to 0. So that means that if we consider the horizontal direction, then V0 component itself is 0. This means that the E dot together with V0 is a cochamp complex of C-infinity vector bundles. And the first condition is VE double prime commutator with V0 is 0. This means V0 and lambda double prime, they are compatible. Yeah. The map and connection are compatible. The non-trivial part is the degree 2 part. It says that lambda double prime square is not 0, but it's plus V0 commutator with V2 is 0. So this means that lambda E double prime is not flat, but is flat up to cochamp homotopy. And this V2 gives the homotopy operator. And of course, we have higher components and higher components. So yeah, so altogether, it gives the flatness of the anti-holomorphic superconnection. And in our talk, all anti-holomorphic superconnections are flat. And we can show that all cohesive modules, it forms a pre-triangulated differential graded category, or pre-triangulated DG category. And this means we have shift by one functor, we have mapping cones, and a remarkable result by Bloch is actually this DG category. It gives a so-called DG enhancement of the derived category, bounded derived category of coherent sheaves on X. Yeah. So yeah, this is the result. So this means that we can use these objects in Bx, which is more differential geometric, to study coherent sheaves, which is in algebraic geometry. Yeah. Okay, and by the way, this theorem requires the complex manifold to be compact, but in a more recent paper, not so recent, 2021 paper, Chang, Holstein, and Lazarev, they generalized this result to non-compact complex manifold, but they need to put some more restrictions on bounded derived category X. Okay. Okay. Yeah, so this is the result of coherent modules. So by the way, I should mention here that we can just this result. So we see that the definition of coherent sheaves is purely local, is through local construction. So definitely that has no hope. There's no hope to just get a non-commutative version of coherent sheaves using its just original definition. But here we see that superconnections, the global sections, infinite sections of vector bundles, all these are very global. So we can expect to replace this by some non-commutative counterpart. And we may get a non-commutative version of derived category of coherent sheaves on non-commutative spaces. Yeah. So this maybe suggests some relation between this work and non-commutative geometry. Okay. So far, is there any questions? Okay. So let's move further. Okay. So now we have the framework, and then we are going to define the Chen-Wei theorem, Chen-Wei theory. So actually, we can have an emission metric on this E dot 2, and we can define a pairing under this emission matrix. And we can then define the conjugates of A double prime under this pairing. So we call it A single prime. And the pairing, the conjugate also decompose into the corresponding component with either V0 dot is goes to EI to EI minus 1, and V2 dot is EI to omega 20 EI plus 1. So by the way, go back to the previous one. We see that V2 is goes to omega 02 EI minus 1, and here is 20 EI plus 1. So we see that the degree doesn't much match very well. So if we define A to be A prime plus A double prime, then the square, we cannot say that is concentrated in omega 1, 1. But we can see that if we take the super trace, it's concentrated in the omega pp. So we get an element in omega equal. And the result is this Chen character form is the theorem closed, and its Bott-Chen cohomology class is also independent of the choice of the metric. And moreover, we can also prove that if the Cauchy complex is exact, then the Chen character is 0 in the Bott-Chen cohomology. And so this proposition, together with some mapping cone construction, we can just obtain a proof that the Chen character map descend to the Grothendieck group of coherent sheaves. So we get a Chen character map from the Grothendieck group to the Bott-Chen cohomology. And we can show that it is a ring homomorphism, and it's kind of easy to show that it's compatible with pullbacks. So that is the Chen character map. That's part of our construction. And I should also, at this point, I should also mention that there are other methods to define Chen character map on coherent sheaves. For example, we have simplicial methods, just using local covers and group together the locally defined Chen characters in some subtle way. So that's by Toledo and Tong and Green and Osgood. And also we have algebraic, or we call it axiomatic method. It's by Grieval and Wu. And Grieval also proves that actually all these constructions must be compatible. There's only one Chen character map from coherent sheaves to cohomology. Okay. Now we are going to prove the Grothendieck-Riemann-Roch theorem. Let's just go back to look at the statement of the result again. The statement is we have this commuting diagram. So we have the push forward of Grothendieck group. We have the push forward of the Bott-Chen cohomology. We have the Chen character map, and the Todd class is just the usual Todd class of the tangent bundle. So let's go into the proof of the result. The idea of the proof is this. First, any holomorphic map can be factorized as two parts. The first is the graphic embedding, and the second is a projection. And we also know that the push forward map is functorial. So in this sense, we just need to prove the Grothendieck group in two cases. First is embedding. The second is projection, and actually it's a trivial projection of the form x times y to y. For these two kind of maps, we need to prove the Grothendieck-Riemann-Roch theorem. The proof of the embedding is relatively easy. First, if the embedding is the embedding of the zero section to the projection bundle, then the derived push forward of cohesive modules could be computed directly using Koszul resolutions. And then we can compute the chain character of the derived push forward, and we can compute the Todd class of the normal bundle, and we just compare two sides explicitly, and we can show that the two sides of the theorem on top of these slides, they are differed by a explicit constructed Bot-Chain exact form. So they are equal in the Bot-Chain cohomology. So it's an easy, it's a, I don't say, I shouldn't say it's an easy check. It's a kind of exercise and to prove the Grothendieck-Riemann-Roch in this special case of embedding. The general case of the embedding is a little bit more difficult, but not too much. The idea in that case is if we X and Y, they are not projective embedding, we can find an X tilde and Y tilde such that the derived the embedding is easier. And X tilde and Y tilde both project to X and Y respectively. And we have the commuting diagram and the pullback of pi X and pi Y, they are injective. So we just need to prove the Grothendieck-Riemann-Roch for embedding of the upper level on the upper level, and then the lower level is obtained automatically. So this idea is called deformation to the normal cone. And we use the functoriality and we just check the special case in the previous slides, and we can just prove the Grothendieck-Riemann-Roch for embedding in a more general case. Yeah, this is a Grothendieck style of proof. Okay, so that's the embedding case. We consider it as an easy case. The projection case is more difficult. I should say much more difficult. Yeah, so this is basically family index theorem. So how do you prove this? If we have a cohesive module on upstairs is in the product space X times S, how to compute its derived push forward? So that's a difficult question. So in general, I should say that it is quite difficult to get an explicit construction of the derived push forward using finite dimensional vector bundles. But it's very natural to get it using an infinite dimensional vector bundle. Yeah, so we're doing it in this way. P lower star, underlying lower star, is the infinite dimensional C-infinity vector bundle on S, and whose fiber is just the sections on the vertical space. So of course it's infinite dimensional. And the push forward of the connection is the same, but we just consider its gradient to be different. Yeah, the trivial example is if E is trivial and A double prime is just a d-bar operator, then the push forward is an infinite dimensional trivial bundle on S, with each fiber is omega 0 dot X. And the push forward of the d-bar connection, we just consider it as a two-part connection. One is the vertical one is d-bar X, and the other is a horizontal one is d-bar S. Yeah. So anyway, it's just we push forward means we to X, we get an infinite dimensional vector bundle on S. And the different part, slightly different part is the conjugate. So if we have a metric on E and also a Riemannian metric on X, then we can just using the two metrics, we can find the conjugate of A double prime. And we see that here, the push forward of A double prime and the push forward and A double prime, they are the same thing.
with different gradient, but the A single prime and the push forward of A single prime, they are different. So one is just the dx plus ds, and the other is the horizontal direction, ds, they are the same, and the vertical direction is the conjugate of the d bar operator. It's not the d operator. Yeah. Well, these two are slightly different. And in general case, the ideas are the same. They just conjugate the push forward A double prime. And using this, we have a commutator of them. We can talk about exponential of them, and we can talk about the super trace of the exponential. And so for this, we need some more functional analysis. So that is, since we are talking about infinite dimensional bundles, we can show that this exponential is in the trace class. So we can also define the Chen character in this way. And our result is this Chen character is also the round closed, and its Bott-Chen cohomology class is independent of the choice of the metric. And also, the most important thing is this Chen character is indeed the Chen character of the derived push forward of the coherent sheaf or of the cohesive module. So anyway, so this shows that the Chen character using these infinite dimensional vector bundles is exactly the object we are looking for. Okay, and now we can prove the Grothendieck-Riemann-Roch theorem using index theorem. I should mention that there is a special case and the general case of the Grothendieck-Riemann-Roch. The special case is it says that the construction of the P single prime, it needs a Riemannian metric on the vertical space X. So just here, X is the vertical space. And since X is a complex manifold, we can form a 1-1 form omega from this Riemannian metric. And the result is if dd bar omega is 0, then we can just rescale the gx with dividing by t, and let t goes to 0. And this Chen character form, as a differential form, it approaches to the integral over x of the taught class and multiplies by the Chen character on x. Okay. So it includes the case that x is scalar, because x is scalar means that the RAM differential of omega x is 0. And of course, it implies dd bar x is 0. dd bar x is 0 is slightly more general than scalar, but yeah. For example, for algebraic surface, I think any complex surface, not algebra, any complex surface, it admits a Riemannian metric such that dd bar omega x is 0. But I don't think, not every surface is scalar. Yeah, so yeah, this is slightly different. Yeah. So I should point out that this is so-called local index theoretic result. So this means that the two sides of equation 4, they are not only equal in the Bott-Chen cohomology, they just has limit as a differential form. Yeah. And the idea of the proof in this case is we just use Gessler's rescaling method and the Leach-Lewis formula, and we just ignore the lower degree terms using the rescaling, and we just compute the limit of t goes to 0 in just explicitly. It's a kind of hard computation, but it's not too involved. Okay, so this is the classic family index theorem, I should say. Yeah. And so some people may ask, what is the limit when x goes to infinity of when t goes to infinity of the same thing? So I should say that if the derived push forward map, the derived push forward of cohesive module is a bounded complex of holomorphic vector bundles of S, then the limit when t goes to infinity is exactly the right-hand side of this as differential form. Yeah. But if the derived push forward is not a bounded complex of holomorphic vector bundles, then the limit of t goes to infinity of this form may not exist. Yeah. But however, it always equals to this in the Botron cohomology. It just may or may not equal to this as differential form when t goes to infinity. Yeah. So that's the special case of the yeah of the Grothendieck-Riemann-Roch theorem in the projection case. Okay, is there any questions on this part or any part before this? Okay, let's move on.
I think, yeah.
Mhm.
Nope, I think it's okay.
Okay, let's move on. Okay, so now the most general case is when we cannot find the matrix on X such that dt bar omega X equals to 0. Yeah, for example, well, maybe we want to consider X such that the dimension of X is greater or equals than 3, just as we said before, complex tori with dimension greater or equal than 3. Then maybe dt bar is not 0. Then this process, it doesn't work. So actually, when t goes to 0 plus, may or the limits of the Chen character form may or may not exist. So we need to think of some new method. This new method is called hypoelliptic superconnections and heat kernels. So the idea is the X actually, if there's nothing much we can do on the space X, but we can think of a larger space, which is the curved X, that is the total space of the holomorphic tangent bundle. And we have this commuting diagram here, where the I is the embedding of the 0 section. So the composition of I and pi is the identity. We are thinking of the derived push forward of P. And using this functoriality construction, we can decompose Rp lower star into the composition of Ri lower star and R pi tilde lower star, where pi tilde is the projection from curved X times S to S. Okay. So in this sense, to study Rp lower star, we can just focus on Ri lower star and R pi tilde lower star. And the first thing is Ri lower star is easier to compute. It's actually an embedding, and this is an easy embedding. We can use Koszul resolutions to compute the Ri lower star. And then the problem is the R pi tilde lower star. Yeah, so this is also pi tilde is the projection from this non-compact total space of X, curved X to S. And to compute this, it seems to be more difficult, more complicated. But the good thing is we double the dimension, so we have more room to wiggle. And the good thing is on this X, curved X, we can define new operator is curved A double prime and curved A prime. Yeah. Their property is, their sum is a hypoelliptic operator in the curved x direction. And it squares, so we see that it's a Laplacian in the vertical direction, but there is also a connection part in the horizontal direction. So it's square is not it's not an elliptic operator, but we can show that it's also slightly weaker, is so-called hypoelliptic operator. And we can still consider its heat kernel and its super trace and its Chen character. And our result is this Chen character is obtained from this very infinite dimensional vector bundles. It's still theorem closed and is independent of the choice of the metric. And also, the Chen character is just gives the Chen character of the simple derived push forward. I think this is RP lower star instead of R pi lower star. RP lower star. Instead of R pi lower star. And we can slightly modify it, and we can even change the omega x, and then we can define the exotic hypoelliptic superconnection. And in this case, we reparameterize it, and we can show that when t goes to 0, we get exactly a Chen character equality, but same as before. So this is the heat kernel proof of the Grothendieck-Riemann-Roch theorem in full generality. But let's just go back to our very first result. So we have this commuting diagram. We have almost no assumptions on the x and y. The only assumption is x and y are both compact complex manifold without boundary, and the F is a holomorphic map between them. We don't assume it's algebraic, or we don't assume they're Kähler, or we have no assumption of the holomorphic map F. We don't assume that the F is projective or something. Of course it's proper because x and y are both compact space. So it's the Grothendieck-Riemann-Roch theorem in a quite general form. Okay. Is there any questions so far? Okay.
Nope, so far.
So, so please. Okay. Okay, so let's talk briefly about some further works. The first thing is, we assume that things are compact, and actually the construction by Chuang and Lazarev and Holstein, it showed that Bloch's theorem can be generalized to a non-compact case. So we are looking, considering the non-compact case of the derived category, the Grothendieck group, and even the Grothendieck-Riemann-Roch. And the second thing is, in my mind, is all the results today, it requires, let me show you. We require that the superconnections are flat. We may ask, what if the superconnections are not flat? Then it depends on what it equals to. And one interesting thing is if it equals to a function, then it will give, we expect that it gives the differential gradient enhancement of the derived category of matrix factorizations on complex manifold. It's a very important, very interesting object in matrix factorization is an interesting object in algebraic geometry. In particular, I think in the so-called Landau-Ginzburg model in mirror symmetry. And also, yeah, this result gives us, since we not only obtain the equality on differential on the cohomology class, we obtain some equality on differential forms, then we expect that we can have more refined results in like Arakarev geometry. For example, like eta invariants and Quillen line bundles, what are the results on this, and other higher structures. And of course, the last thing I am considering is, yeah, do we have non-commutative generalization of this? I know that like Ray working, yeah, has done a lot of work on non-commutative holomorphic structures on non-commutative complex geometry on flag manifold. So yeah, it will be interesting if we can find some, yeah, non-commutative analog of all these results on non-commutative complex spaces. Yeah. Okay, so that's what I'd like to talk about today. And by the way, so here are some references. So our book is here, is coherent shift superconnections and Riemann-Roch Grothendieck. Yeah, and the work of Bloch is very inspiring, and yeah, its duality and equivalence of modular categories in non-commutative geometry. Yeah, and yeah, the Bloch and Chang, he constructs the Bottom characteristic forms in his PhD thesis. And yeah, we have, yeah, these are the result. And the result of Chuang, Hochstein, and Vatrov is also here. And result of Vazan is in her favorite famous paper, counter example for the Hodge conjecture. Okay, so that's it. Thank you.
Thank you very much, Zhaoting, for a very informative talk. So do we have questions? If not, I'll start with something. So you're saying that for a Kähler manifold, the Bott-Chern cohomology and the de Rham cohomology coincide?
Yes, that's true. Yes.
So then why do you consider for a non-Kähler manifold, why do you consider the Bott-Chern cohomology? What advantage does it have over ordinary cohomology?
Yeah, it's more refined. The Bott-Chern cohomology is more refined. We see, let's see, show you the definition. Yeah, you see the definition. The Bott-Chern cohomology, of course, cohomology is something quotient by something else. And Bott-Chern cohomology, the something is the same. They are closed forms, but the something else is actually smaller. Now, if we just consider ordinary cohomology, then that's de Rham closed quotient by de Rham boundary. But here is quotient by DD bar of something. So this thing actually is smaller than just de Rham boundary. So yeah, of course, the quotient, the denominator is smaller, so the quotient is more refined. Yeah. So this Bott-Chern cohomology in the non-Kähler case, it's a more refined invariant than the ordinary cohomology. So yeah, that's the case. Of course, yeah, lots of interest in complex manifold is Kähler, but still there are some non-Kähler complex manifolds. Yeah.
Of course, yeah.
So,
so is there some spectral sequence relating the Bott-Chern cohomology to de Rham?
Yes, so that is true. So yeah, that is true. But yeah, the actual relation is quite subtle. There are a lot of works on this. Like they have very subtle relations between them. Yeah.
And then I guess in addition, like from your last comment about the non-commutativity, I'm trying to see where the problems arise first, because we have omega 0, 1 are anti-holomorphic forms. We have connections. That means you have holomorphic vector bundles. then I guess the notion of sheaf is always
challenge is,
subtle, but
maybe we don't have this. This result for block may or may not exist. So that depends on our definition of what is the BX, what is the coherent, what is the bounded derived category of coherent sheaves? Are they equivalent? Maybe you can say that we
Tell me
define.
what the homotopy category is?
Mm-hmm.
What is the homotopy category precisely?
You mean what's the definition of the homotopy category of maybe I can just share. Oh, maybe I can call it space. Maybe here, maybe more space. A homotopy category. By the way, do you know the definition of
it's
DG
going to be
category?
basically a category enhanced over DG.
Yeah. That is so. If I have a call, if